So we're going to go ahead and continue our theme of extending Newton's second law to systems where it's a little too complicated to use directly. And here we'll be looking at thermodynamic systems, which is ensembles of very large numbers of particles. So in principle, you could use Newton's second law of motion for each and every particle in some gas, let's say, but the problem is you'll be looking at on the order of 10 to the 23rd individual particles that you'd have to model this for, and that gets really rough. So we will take, over the next few videos, we will be taking Newton's second law, obtaining the ideal gas law, and then exploring other bits of thermodynamics, which rely mostly on the assumption just that particles interact without really saying too much about how they interact. But first we need to lay some groundwork, and so we'll start with a quick review of the phases of matter. Now, I'll neglect plasmas here because we're not too terribly interested in what's happening on the surface of the sun or something like that. We'll just look at the big three: solid, liquid, and gas, and give the usual definition. So usually we say that the solid is that state of matter where the matter occupies a definite volume and has a definite shape. A liquid will have a definite volume, but the shape is determined by the container. For a gas, both the volume and the shape are determined by the container. Now, researchers will extend these out, but these are the big three. But say, for instance, with water, they'll point out that there are actually multiple different solid phases of water, depending on the pressure and the temperature. And that has to do with the fact that the solid phases of water can have their molecules arranged in different shapes. So that counts as a phase two, but we're just looking at the big three phases at the moment. So just to remember some vocabulary for when we're changing between phases. So solid, liquid, and gas. So if a solid becomes a liquid, we will say that that process is melting. So we melt. On the other hand, if we go from liquid to solid, we say that we freeze. Similarly, if we go from liquid to gas, we boil. If we go from gas to liquid, we condense. And it is possible with certain molecules, depending on the pressure, to go straight from solid to gas. For instance, carbon dioxide at atmospheric pressure does that. That's dry ice. So if as the solid carbon dioxide in the dry ice becomes gaseous carbon dioxide, we say that it sublimes. And when you're making dry ice by taking carbon dioxide gas and turning it into a solid, you say that you depose into a solid. Or the process is deposition. All right. And so what's happening in each of these is that we'll find that when, say, you go from a solid to a liquid, what's happening is you have to input energy into the system. And what you are doing is you are breaking some of the atomic bonds that are keeping the solid held together in its molecular structure, in order to allow for the molecules to move more freely. In a solid, the molecules tend to be arranged rigidly in a lattice, like so, where I'm representing the bonds of springs. In a liquid, there is still interaction between them, but and the spacing stays roughly the same. But what happens now is that, unlike with the solid, the atoms now have the ability to swap positions with each other, which you did not have before. So overall, we had to input energy in order to break this more rigid bond structure to allow for, there's still attraction between the molecules, but we're allowing for there to be some motion of the molecules within the substance. Going from liquid to gas, even that weaker attraction, say I'll indicate those weaker attractions with dotted lines, even that weaker attraction winds up getting broken. And so energy has to be added to the system again to make that happen. And so you just have molecules flying off in any random direction. And the only thing that's keeping it from running away altogether is occasionally bounce off the walls of the container in order to keep ping-ponging back and forth. So one of the things that you generally observe when you go through a phase transition is that the temperature will remain a constant during the transition. As we developed in a future video, the zeroth law of thermodynamics, we'll be able to say a little bit more about what's going on with that. But again, as for part of our just laying our groundwork here, need to introduce or revisit our friend the mole. And the mole is one of these things that got affected by the 2018 redefinition of SI. So the mole is now defined by Avogadro's number being an exact number. It is defined to be exactly 6.022140765 times 10 to the 23rd, and the units are inverse moles in order to make stoichiometry work. And this is an exact number. So the older definition of the mole was, it was the number of carbon-12 atoms in 12 grams of carbon-12. And so under the old definition, you could say that the atomic mass, well, it's still correct to say the atomic mass unit, which the symbol for an atomic mass unit is U. It's still the mass of a carbon-12 atom, and you put the isotope in front of the letter, over Avogadro's number. This works out to be 1.6605 times 10 to the negative 27 kilograms. Now, it used to be the case that if you had a mole of anything, that would amount to taking Avogadro's number, multiplying it by the atomic mass unit, and getting 1 gram exactly by the definition. Now, technically, it's approximately 1 gram, but it's really darn close to equal. And this is because the current definition of Avogadro's number is based on the absolute best ability to measure how many carbon-12 atoms there are in 12 grams of carbon-12. However, you can see that for us to get down to the exact number, we'd have to have 23 significant figures, and we don't. So with this now being the definition of Avogadro's number, with a more precise measurement of how many atoms are in carbon-12, we'll find out that 12 grams of carbon-12 will almost certainly be fractionally more or less than a mole, but we're talking that this is going to be in at least the 11th significant figure. So for practical chemistry use and practical physics use, this isn't usually going to matter. However, this does lead to a plethora of ends that show up in thermodynamics. And so it's time to just decode all the ends to make sure we're on the same page. So lowercase n in thermodynamics is defined to be the number of moles of something you have. Now, this doesn't apply purely to atoms and molecules. You could talk about having a mole of bricks. You could conceivably have 6 times 10 to the 23rd bricks lying around somewhere. You do that, it's probably going to collapse in on itself and implode horribly from its own weight, but you could talk about it at least. But it's not practical to have 10 to the 23rd bricks lying around, but having 10 to the 23rd atoms of something lying around is very common. And so it's very useful for chemists because 1 mole of carbon-12, for instance, weighs 12 grams. That's nice practical numbers to work in. So the mole is just a nice convenient way to express large numbers of atoms using a smaller number. Capital N is the number of atoms or molecules. Or I suppose we could talk about bricks too if we really wanted to, but we don't really want to. And the way I keep this straight is this is always going to be a bigger number than the number of moles by a factor of 6 times 10 to the 23rd. So the big N goes with the big number, and the little n goes with the little number. They're both representing the same number of atoms. It's just here it's in moles. Here it is just plain a pure number, no unit. Na is again Avogadro's number. Now, I bring this up because physicists tend to focus much more on the big N rather than the little n. As we work to obtaining the ideal gas law from Newton's second law, we'll be looking directly at how individual atoms interact with the walls of a vessel that they're in. And so then if we want to talk about an ensemble of them, it makes sense to just talk about however many atoms you have. So it's just because we're focused on the atoms and not the grams that it makes sense for physicists usually to work using big N. However, we have to compare with chemical literature, and sometimes we're doing our own chemistry as well. Or we do things that are chemistry adjacent, and so we will also be using the little n for the moles, but the bigger focus will be the big N. However, we'll sometimes have to write equations 2 different ways to account for that. We'll see that as we go along. But just as a quick review of the sort of thing that you would have typically seen in chemistry, let's say you were given a problem where you were asked to find the mass of half a mole of carbon dioxide. Well, one of the things you can look up is the atomic masses of each of these. And so you look up the atomic mass of carbon in the periodic table, and you get 12.011 atomic mass units. You say, wait a minute, didn't we just say a mole was 12 grams of carbon-12? Yeah, 12 grams of carbon-12. But other isotopes are present, not just carbon-12. And so the number in the periodic table is based as an average of over all the isotopes according to natural abundance. By the same token, the atomic mass of oxygen is 15.9994 atomic mass units. Now that number may seem extraordinarily close to 16, and you would be right. An even earlier definition of the mole actually was based on oxygen rather than carbon, and the number 16 rather than 12. But eventually it was transitioned from oxygen to carbon, and there you go. And now it's just plain a number. So the idea is you go ahead and find yourself the mass of a mole. Well, 1 mole of carbon dioxide, you'll have 1 carbon, 2 oxygens. So a mole of carbon would weigh 12.011 grams. This is because with molar mass, you can always say the mass of a mole of a thing is the atomic mass, but replace the atomic mass unit with grams to get a molar mass. And similarly, we'll have 2 mole in a mole of carbon dioxide. You'll have 1 mole of carbon, 2 moles of oxygen atoms. So it'll be 2 times 15.9994 grams. And then you say, oh, wait a minute. I actually wanted half a mole, not an entire mole. So we'll have to multiply the whole thing by a half. And we get that half a mole of carbon dioxide has a mass of 22.0049 grams in natural abundance. So, alrighty there. So in the next video here, we will start to get down to brass tacks and talk about temperature and the 0th law of thermodynamics. Catch you over there.